Hello gang, ready for video number 4 in our matter journey. Really, we can almost call it 3B because this is just an extension of classification of matter. So if you look at that table we made in the last video where we took matter, we could have pure substances, mixtures, homogeneous versus heterogeneous mixtures, we could have elements or compounds, and we broke elements up into monatomic elements and polyatomic, specifically diatomic elements. Remember the Magnificent Seven or Brinkelhoff. And then with compounds, they could be made up of molecules or molecular compounds, sometimes called covalent compounds, or they could be made up of ions, which we would call ionic compounds, with very different chemical and physical properties. We'll get into those later. If you want to do this, you could draw this from that table where we had mixtures here and pure substances there. If I want to go from the mixture and separate it into its pure substances, which is really common in the industrial world because very few substances exist in the pure state in nature. You might find some noble metals like gold or platinum, some noble gases like some elements like argon and krypton. You'll see them in the pure state, and that's all fine and dandy, but most metals react with oxygen, some of them with sulfur. Most things are going to be reacting, especially when you got 21% of the atmosphere is oxygen. It's very exposed to it. So, for example, let's say you want aluminum, right? We want to make aluminum. Maybe we want to start a business, making aluminum cans or some aluminum products or something. Back in the day, aluminum was very expensive. It's kind of cheap to us now. We're like, yeah, aluminum can, whatever. And we try to recycle to save some money if we can. And I'll tell you why it saves so much money as well. It's expensive to extract it out of its ores. Because in nature, aluminum is not a pure, it's not a noble metal. It reacts with oxygen. You get aluminum oxide, which is part of an ore. I think it's called bauxite or something, B-A-U-X-I-T-E. So if we want to purify aluminum, make aluminum cans, or to make utensils, forks or whatever, it takes a lot of money to take the ore, dig it out of the earth, extract it out, get the compound aluminum oxide, right? So we got to separate this into its pure substances, extract everything out just to get the aluminum oxide. Then we got to take that compound and separate the oxygen from the aluminum, which is chemically combined, and create the element. That's a lot of, in today's world, that's a lot of electricity we're going to need to do that, a lot of power, a lot of energy. So, back in the day, when everything was gold and silver and, you got silver spoons and all that fun stuff, I'll tell you, to have an aluminum spoon back in the day, you'd have to be royalty to do that because gold you can just dig up from the ground and, it's malleable, you can make it into a spoon. Yeah, it's pricey, but not like aluminum. So if you had aluminum forks, woo! You were the dude or dudette of society. I'm telling you, you go to dinner and they pull out their aluminum utensils. They're like, whoa, you're rich. Everybody's got silver spoons. Today, that's completely flipped. Who knows, in our lifetime, some things that might have been valuable for the last 100 years become irrelevant because of some kind of technical innovation, right? That makes it easier to extract out. But you can see how industry works, right? So I got to take the mixture, break it up into its pure substances. If that pure substance is a compound, I want to break it up into its elements, yada, yada, yada. So it's exceedingly expensive to extract aluminum from its ore, right? But if you can take something that's already made of aluminum, like an aluminum can, and just melt it down and recycle it into something new, that takes a tremendously less amount. That verbiage wasn't good. A lot less, I like that word tremendous, a lot less energy to make, say, aluminum cans from recycled aluminum than to extract it from its ore going through these processes, right? Saves a lot of money and allows us as consumers to get things that are, so cans are less expensive when you do that. Cool. All right. So again, mixtures are physically mixed, right? So, and they can be mixed in any proportion, and it doesn't matter what proportion they're mixed. We can separate them, since they're physically mixed, we would need a physical separation technique. And you can write that up on your chart if you want to. We've got the two boxes. You can just put a little arrow there and put physical separation technique. If you've got a compound, well, we know that's two or more elements chemically mixed or chemically combined in fixed proportions, right? There's a fixed proportion. Well, to separate those out, since they're chemically combined, we need a chemical separation technique. So this particular video is going to look at mostly different types of physical separation techniques, and you'll probably do some of these in lab. They're much easier to do, takes much less energy. And chemical separation techniques, we might do a little bit of that because it requires a bit more energy. At this level, we're probably not going to be shooting things with laser beams, right? So if you're a chemistry major, All right, when I was teaching, the higher level analytical stuff, we got to blast some things with lasers. Lots of fun. Chemists have a natural destructive tendency. It's like, pow, yeah, it was so cool. It was so much fun. So we won't be shooting this with laser beams at this point, but it's fun. So let's start with the physical separation techniques. You're probably familiar with all of them. And the specific technique we'll do on a video in lab. All right, we're just I might briefly talk about it, maybe draw it up on the board, but I'm not going to physically perform it here because I'm not in my lab right now. All right, let's start with the physical separation techniques. Again, going from a mixture to its pure substances. It's not specifying the extent that is. Is it 100%, separation, 90% separation? We haven't specified that yet. Just that we're somehow physically able to separate these out. So we'll look at filtration. Probably the most common one we'll do in the general chemistry level or introductory chemistry level. You've probably done some filtration, so we'll talk about that one in a bit of detail. Decantation, right? You've probably done that at home. It's kind of a poor version of filtration. We'll talk about distillation, my personal favorite right there. I'll briefly talk about chromatography. I could do a whole class on chromatography. It's crazy. Probably the best separation technique, but you may not see chromatography in the general chemistry level, maybe at organic, but the higher levels you get in chemistry and in science in general, you'll be doing lots and lots of chromatography. So we'll briefly talk about, especially the first three. I'll spend a little bit of time talking about chromatography, and there's a whole bunch of other ones specifically on like physical property differences. It really comes down to the fact that there's different physical properties between the two or more physical substances. So solubility differences, right? Maybe I have a mixture of two solids, one dissolves in water, one doesn't. Put some water in there, one dissolves, the other doesn't. And then we'll find out that I can filtrate that and the solid and the liquid separate out, right? Pretty easy to do. Magnetic differences. Maybe I have two solid powders mixed together. One's magnetic, what is it? Take a magnet, bloop, the magnetic one comes out. Yay, proper separation, right? So anything with two different physical properties that I can, take advantage of. We're off to the races. So let's start with filtration here. Pretty sure you've all done a filtration in your life. Maybe, maybe not. I don't know. But if you make coffee in the morning, right? I'm not a coffee guy. I'm a tea guy. But I guess with coffee, you got to put in a coffee filter or something so that just the liquid comes through and the coffee grinds or whatever. Can you imagine that those little pieces of the coffee beans get choking all over it? Wouldn't know. I've had like 3 or 4 cups my whole life. But let's say we've got some kind of mixture in a laboratory or whatever as a chemist. It's the same idea. What we're going to do is we're going to take it's for heterogeneous mixtures only, where you've got a solid. So it could be a solid in a liquid. Maybe you formed some kind of precipitate inside, floating little particles of precipitates floating inside water. Could be particles like smoke in air, right? So it could be in mixtures, could be any phase, right? So it could be a solid, liquid, gas. Doesn't matter what the physical state is of those pure substances, whether they're solid, liquid, or gas. But if you've got solid particles in a gas or in a liquid, we can separate those out using filter paper, right? You can't see the holes in there, but that has little tiny holes that liquid could get through, but the solid cannot. Hey, and you can get different types of filter paper with smaller holes or bigger holes, or an orifice if you want to call it something specific. So it's used, we could not separate a homogeneous mixture with this, which is called a solution, by the way, so like salt water. Because if it's a homogeneous mixture or solution, it's all in the liquid state, all of it would go through, right? So all of the pure substances would go through, and you couldn't actually physically separate them. You'd need something else, like distillation, to separate that out. So let's say we got a beaker, maybe you got a mixture of a liquid with some particles in it, and we want to separate them out. So what you do is just get your glass funnel. Hey, it could be a plastic funnel, whatever. Usually you'll have a ring stand, and that just fits right in the ring stand. Clink, pop it in there. And what I like to do is I like to take that filter paper and fold it up into like an ice cream cone. Woohoo! And then it opens up real nice. And then it just pops right into your filter paper. The filter paper fits right into your funnel. And I'll spray that down with some deionized water. Otherwise, poof, it pops back out again, right? So I'll spray that down with some DI water. We'll do a video for that in the lab. and that sits inside there. So that green stuff, they say we have, not like our filter paper is green, but white doesn't work on a white board. Pop it in there, and then I can just take my mixture, pour it through. Well, obviously the liquid's going to come through, so I need something to catch it. So some clean device, usually a beaker. So I'll have that suspended. I don't want it up too high, but I want it suspended in there. And so I'll pour it in. The liquid goes through into here. We call that the filtrate. And then the solid would stick in there. And then later on, I could, dry this out. Maybe I weighed this ahead of time. I could weigh it after and measure the mass increase. I can measure the mass of the solid produced, or somehow I could separate them out. Right? So if I poured that through, the liquid would drip out, right? And we call that the filtrate. Now, maybe that's what you're after instead of the solid. I don't know. But more commonly, you're after the solid, and then you dispose of that filtrate in some way. Hopefully not down the sink, unless it's allowed to go down the sink. And then the solid would get stuck in that filter paper. Pretty simple technique. And you could repeat that cycle. Say some gets through, you could repeat that cycle over and over and over until you get what you would hope is 100% separation. But again, that's heterogeneous mixtures containing solids, so it's got some restrictions on it. Doesn't work for homogeneous mixtures, which is what we would call a solution. All right, pretty straightforward. Let's do decantation. I don't know if you've ever decanted anything. You may have and not even known you've done it. So let's say we've got a heterogeneous mixture with a solid and a liquid in here. We want to separate them out, but we don't need a complete separation like a filtration. So we can just kind of do a, kind of a half-butt separation. So it's like filtration, but without the filter paper. It's not complete though. Nowhere near as complete. So I'm not going to use the filter paper. I'm just going to use the stirring rod. So I'll have my collection beaker, or whatever container it is. I'll have my stirring rod here to guide it, and then I'm going to pour, literally what I'm doing, I'm just going to pour liquid out without letting the solid come out. But sometimes when you do it slow, you ever done that where you go to pour something, and instead of the liquid going like this, it goes blah, blah, like if you ever change oil in your car, and you go to pour it in there, and it goes blah, down this way, and you're like, oh, it gets all over the car engine, your hand. I hate it when that happens. So if you take your stirring rod, set this up here and pour it on there, the liquid clings to the stirring rod and then flows down into there. So as you pour it, if this would be my filtrate of the liquid, that would flow down the side and then drip down in to give me my liquid there. And so you pour until just before the solid comes out, and they go, oh, right, as some solid gets out, you pour it back in, start over again. So you're getting a good separation, but nowhere near a complete separation. So it's a real quick, really cheap, costs you nothing once you got, your stirring rods and your beakers and stuff. I do this all the time. My favorite example is my morning breakfast is I take sourdough bread, put it in the toaster oven. When it's all done, bing, slather it with creamy peanut butter, and then I put sliced pickles on it. Oh, yum, 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 so good. Don't knock it till you try it. No extra credit. But because I eat that so much, we get these big old jars. I mean, they're huge buckets of sliced pickles. Well, once you're, you can get those sliced pickles out of the top, but once you're halfway down, now you're trying to fish these stupid pickles out, like with a knife or a fork or something. It's like they're floating all over the place. It's kind of a pain in the butt. So what you got to do is take this big pickle jar, and what I do is I try to pour some of the liquid out, but when you do that, the pickles start coming out into the sink. You're like, I need those pickles. Right? So what I do is I'll take a fork or a knife, put it on the edge of the pickle jar, and pour it. The pickle juice comes out, but the pickles stick against the fork so the pickles don't come out. That's decanting my pickles from the pickle juice. You've probably done something like that. So anyway, you'll probably do this a couple times in the lab, and hopefully you'll be able to get to do a filtration as well. Let's look at the big one, distillation. All right, distillation. This you could use for almost anything, but it's more expensive than filtration and way more expensive. The decantation really doesn't cost you anything. Filtration, you got to buy the filter paper, but you're using gravity, right? Gravity filtration, so really makes it cheap. Distillation requires some energy, so it's going to cost you a little bit. But if you have a homogeneous mixture, aka a solution, how are you going? You can't separate that using filtration and decantation. It's impossible, right? Because if it's a liquid, everything goes through the filter paper, so it's worthless. So this is useful for homogeneous mixtures or solutions and heterogeneous mixtures. But for a heterogeneous mixture, if it has a solid, just go ahead and do filtration or something that's easier. But you could distill it. Hey, it's really fun to do. Won't be able to do the demo here. This is going to take advantage. Remember, these pure substances are physically mixed. So we need to separate them based on different physical properties, right? So boiling point's a physical property. So if I have a mixture of two liquids, right? So say you take some vodka or something like that, or spirits, and you've got alcohol in there and water, but maybe you've got too much water. You want to get rid of some of the water, and you want to increase the percentage or proof of that particular spirit, right? Well, what you do is you look at the fact that they have different boiling points. Water is a different substance than alcohol, so they have different physical boiling points. Well, if those boiling points are different enough, I could heat it up. The one with the lower boiling point turns into a gas, right? You heat it up until it's gone. And hopefully the boiling points are so far apart that you can get rid of almost all of the one with the lower boiling point. Now, if you have a solid with a liquid, just heat it up. Right? If you got sand with water, just heat it up until the water vaporizes away and you're left with the sand. If you've got salt water, heat it up. The water vaporizes, you're left with the salt. You'll actually see the salt re-solidify out. And then you can keep the salt, but if you want the water, you got to, I'll draw a picture of the apparatus. If you want the water, you'd better collect it before it disperses out into the atmosphere. That'd be a problem. Like if you're, stuck on an island dying and you need some pure water, you can't drink ocean water. But if you heat it up, you can vaporize the water and separate it from the salt, but somehow you got to collect the water. Otherwise, it's pointless. You don't want the salt. But mostly you'll use distillation for a liquid homogeneous mixture, right? So either two or more liquids or salt water or something like that. So let's draw the apparatus, but you get the basic premise: two different boiling points, different enough where I could heat one and vaporize it, and the other one does not. Separation accomplished. Very overly simplistic view of distillation here, all right? So let's say we've got some kind of, see my ugly Erlenmeyer flask there? So we could have salt water there. We could have a mixture of two different liquids there. Like I said, like I talked about vodka or something like that. So if you want to, this was common in the moonshine industry, especially back in the Prohibition days or something like that, where it was illegal, right? So you don't want to be shipping around a horse wagon full of, say, 10 barrels of alcohol that's, say, 10% alcohol, 90% water. You're shipping mostly water, so it's more expensive and you're more likely to get caught. So wouldn't it be smarter to just get rid of the water? Nobody cares about the water. So heat up your liquor, try to separate the alcohol from the water. Unfortunately, the alcohol has a lower boiling point than the water, so if you just heat it, you lose the alcohol, right? But you do that, and what you can do is you can intensify the amount of alcohol to the point where you could get maybe a 90% alcohol, 10% water mixture. So instead of 10 barrels, maybe you're down to 1 or 2 barrels. Much easier to sneak through in the black market during Prohibition days. But you hear about moonshine and moonshine distilleries, things like that. You've probably heard of petroleum, right? Being put through a distillation tower or something like that. Fascinating. We'll take the whole bunch of it, heat it up. The ones that have the lowest boiling point, boil off, move higher and higher up, and are extracted down these side tubes. Ones that are kind of medium level extract over here. So you get like your methane gas, your ethane gas. You might get your octane fuel, and then on the bottom you get the sludge and the coal tar and all that junk. So you can look up those. This is just an overly simplistic view of what distillation is, just heating it up. So let's say we have this mixture with a heat source. So I could put it under a Bunsen burner. I could put it on a heating plate, a hot plate, whatever, a heating jacket. However you heat it up, you're heating it above the boiling point of substance number 1, but below the boiling point of substance number 2, right? So what's going to happen is you're going to vaporize up into here. So there's substance number 1 as a vapor or gas, and that has the lower boiling point. So if that was salt water, obviously the water has a lower boiling point than salt, so the water goes. If that was an alcoholic beverage, the ethanol would go and the water would stay. You always get a little bit of water in there, so you can never really get 100% alcohol, 0% water. So there's always going to be a little bit of water in there. But if you take the percent alcohol and double it, that's the proof, right? So if it's 40% alcohol, 60% water, 40% times 2 would make it 80 proof. Some really cool historical stuff on there. Yeah, light it on fire, it's proof there's enough alcohol in there. Fun, history's just great. But anyway, so now my vapor travels through here, but it's a vapor. And if that's my water, say it was salt water, and I want to collect the water to drink, I can't just let it dissipate. I need to cool it down and recondense it. So you can think of these as condensing coils. So maybe it's some glass coils where we take some cold water from a faucet and it just cycles around and it cools the vapor. So the vapor is moving in here and then it starts condensing back into the original liquid, and you got the pure water. Woohoo! Yay! Right? Or it could just be like a cold jacket or something, whatever works. Just something that brings the temperature of the vapor down below its boiling point so it recondenses back into a liquid, drip, drip, drip. And then I'll have my pure liquid here. And then if it was salt water, I'd be left with a cake of salt there. If it was the alcoholic beverage, the alcohol would be over here. The water would be over here. And you could redo it over and over and over and get some pretty darn good separations. But you're heating it, so that costs you some moolah, right? Unlike filtration and decantation. Moving on. For chromatography, again, you know, if you move on to analytical chemistry, you probably might even take a whole class on this. It is by far the most common separation technique I'm aware of on the planet. But I just want to give you a glimpse. You probably did it in biology. We won't do this in general chemistry, but you might have done some paper chromatography in biology where you took like an ink, you know, you took a little strip of paper, put an ink blot there, set it in a beaker with some water, and the water traveled up the paper, right? So in this case, the paper is called a stationary phase, right? And the water is so the ink dissolved in the water is the mobile phase. It's moving, and the water and the ink travels up. And what happens, the different components of the ink move at different rates up. So you might see like a reddish color move up higher and a yellowish color here and orange color. You see the colors separate because those are different species, different substances, and they separate out based on distances. The way I didn't do paper chromatography, I did things like gas chromatography, liquid chromatography. A lot of times you have this really long tube, like a metal tube or a glass tube or something like that, coated with a chemical on the inside. It's amazing how they can do this. Some of these tubes are, you know, so thin you can't even see the tube anymore. And you can have this substance, you convert it maybe into the gas phase or mix it with a liquid, and you move it through the tube so it's forced to travel down this tube, which could be, you know, 10, 15, 20 meters long sometimes. Maybe it's this long, maybe it's 50 meters long, doesn't matter. And what happens is the mixture you're trying to separate is in this, it's in the, you know, dissolved in a liquid or converted to a gas, and a gas is used to push it down so it moves through that tube, so it's exposed to that stationary phase chemical. That's how they do that. It's truly amazing. And then your mixture, of course, is in the mobile phase, so it's moving down this tube. And some molecules, so maybe you got 10 different substances in that mixture. Well, based on their chemical and physical properties, some will be more attracted to the chemicals in the stationary phase coated inside the tube or on the paper, and some are more attracted to the mobile phase, the solvent or the gas or whatever. And so it moves through. The ones that are more attracted to the stationary phase move slower, so they separate out. The ones that are less attracted to it move faster. And so you'll get this. So if this is substance 1, substance 2, they start at the beginning and they go, this one's more attracted to the stationary phase, this one isn't. So what happens is this one moves faster as they're moving down, and you get this distance separation. So you can get what's called a chromatogram at the end, and it spits out the tube, and you might have another collection device to identify those. So you'll see things at the higher levels like GCMS, gas chromatometer. You use a gas chromatography to separate it, and a mass spectrometer to catch them and identify them and measure the amount and possibly even the identity of them. It's really, really cool. So I'm not going to go any details or show you a pretty picture or anything like that. It's just different molecules of different substances in the mixture moving at different speeds because some are more attracted to the chemicals in the stationary phase, some are less attracted. It's a simplistically beautiful, and I wish I could spend a whole day on it, but I can't. Let's do some chemical separation techniques real quick, and we'll be done with separation techniques. Right, chemical separation techniques, of course, are used to take compounds, which are two or more elements chemically combined in a fixed ratio, and to break them apart, like the aluminum oxide. I don't want just the aluminum. It takes a lot of energy to break those chemical bonds that hold those elements together. So they're used to break apart, or if you can think of it as decompose the compounds into their individual elements. And I've seen several different ways to do this. There's not really names for them like distillation or filtration or something, at least what we're going to use at this level. But remember, this requires a lot more energy because we're chemically separated. We're breaking these chemical bonds. We're not just physically separating things. One that is a lot of fun, one of the original ones, was using high voltage for water. When they thought water was an element, right, back in the day, and you just put high voltage in there and you have these electrodes in there and you see bubbles form, and bubbles of oxygen gas go to one side and bubbles of hydrogen gas go to the other side. And you can collect them, and they realize, whoa, water's not a pure substance. I mean, well, it is a pure substance, but water's not an element because it contains two different elements, oxygen and hydrogen. Right? That confused people for quite a while. And you can see the volume ratios. It's a neat little experiment. Lasers, my personal favorite. Pow, pow, pow. I use these pulse lasers and blast holes through, items or whatever. But you can use it to apply energy and decompose something into its component parts, right? Probably the one you'll use if you do it in general chemistry will be using high heat, which is called thermal decomposition. So you just take a compound, heat it up. That increases the jiggling of the particles until the point where you break those forces that hold those particles together. Bam, and you now have your separated elements. Right? Not too hard to do, you're just applying energy to it. So that's enough for separation technique. You can read more details in your textbook or whatever. Let's move along our journey.